Introduction to Subsets of Real Numbers. So let's begin our exploration of subsets of real numbers. This first slide introduces a foundational concept: sets. Now, what is a set? Simply put, a set is a collection of distinct objects. By distinct, we mean that each object within the set is unique, no repetitions allowed. These objects can be absolutely anything. They could be numbers like 1, 2, and 3. They could be letters like A, B, and C. They could even be colors like red, blue, and green. And believe it or not, a set can even contain other sets within it. We'll get to that a bit later on as we progress. The way we denote or write down a set is using curly braces. That's these symbols. Everything inside those braces represents the elements that belong to that particular set. Let's look at an example. Here we have the set of vowels. It's written as a E, I, O, U. Notice how each vowel is listed once, separated by commas and enclosed within the curly braces. This represents the collection of all vowels, a very simple but important set. Understanding sets is crucial because the idea of subsets, which we'll be diving into next, builds directly on this concept. So, make sure you have a firm grasp of what a set is before we move forward. What is a subset? So let's move on to understanding what a subset actually is. As we discussed on the previous slide, we have sets, collections of objects. Now, a subset is essentially a smaller group taken from a larger group. Think of it like this. If you have a box of crayons, a small handful of those crayons would be a subset of the entire box. More formally, mathematicians like to be very precise. We use symbols to represent these ideas. So, if we have two sets, let's call them A and B, then A is a subset of B, and we write that as A is contained within B, using this symbol. A subset B. It looks like a smaller b with an equal sign underneath. What that symbol means is that every single element, that is, every object that's inside set A, must also be found inside set B. If even one element in A is not in B, then A is not a subset of B. This concept is crucial because, as we'll see in the following slides, we'll be applying this to the set of real numbers, breaking it down into different, important subsets like even numbers, odd numbers, and so on. Understanding this definition of a subset is the foundation for all of that. So, make sure you grasp the idea that every member of the smaller set must also be a member of the larger set for it to be a true subset. The set of real numbers. So let's move on to slide 3. The title here is the set of real numbers. Now, remember we just talked about sets and subsets? Well, the real numbers form a very important foundational set in mathematics. We denote, that means represent, the set of real numbers with a special symbol, a capital R, and it looks like this, R with a double bar through it. We call it R double bar, and it represents all the numbers that can be shown on a number line. Think about a number line. What kinds of numbers live on that number line? Well, you've got positive numbers, numbers greater than 0, like 1, 2, 3, and so on. You've also got negative numbers, numbers less than 0, like -1, -2, -3, and so on. And right in the middle, we have 0. But it doesn't stop there. The real numbers also include fractions. Things like 1/2, 3/4, -2/3, any number that can be expressed as a ratio of two integers. Then we have decimals. These are numbers with a decimal point, like 3.14 or -0.75. Decimals can either terminate, meaning they end after a finite number of digits, or they can repeat, meaning a pattern of digits goes on forever. Finally, and this is where it gets a little more interesting, the real numbers include irrational numbers. These are numbers that cannot be expressed as a simple fraction. They have decimal representations that go on forever without repeating. Two very famous examples are the square root of 2, that's written as root 2, and pi, which is approximately 3.14159, but the digits go on infinitely without any repeating pattern. So, to recap, the set of real numbers encompasses all of these: positive numbers, negative numbers, 0, fractions, decimals, and irrational numbers. It's a huge collection, and understanding it is crucial as we move forward and start looking at specific subsets within this set, which we'll cover on the next slide. Subsets of real numbers. Now, within this massive set of real numbers, we don't just leave things as one big group. We actually identify important subsets. Think of it like organizing a large collection. You wouldn't just throw everything into one pile, right? You'd create smaller, more manageable groups. These subsets group numbers together based on specific characteristics they share. They have something in common that sets them apart. Let's look at an example. Consider the set of even numbers, which we represent as 2, 4, 6, 8, and so on. Notice the curly braces, that's how we denote a set, as we learned in slide 1. This set contains all the whole numbers that are divisible by 2. Now, is this set of even numbers a part of the larger set of real numbers? Absolutely. Every even number is a real number. Because every element within the set of even numbers is also an element of the set of real numbers, we can confidently say that the set of even numbers is a subset of the real numbers. So let's move on to slide 4. As we discussed in the previous slides, the set of real numbers encompasses all numbers you can find on the number line: positives, negatives, zero, fractions, decimals, and even those irrational numbers like the square root of 2 or pi. We'll be exploring many of these subsets in more detail, like integers, rational numbers, and irrational numbers, and understanding why categorizing them this way is so useful. As we'll see on the next slide, this organization isn't just for neatness. It actually impacts how we perform mathematical operations and solve problems. Why are subsets important? Think about it, mathematics deals with a lot of different numbers. By grouping them into subsets, like we saw with even numbers, or we'll see with integers and rational numbers later, we create a system for organizing and categorizing them. This makes everything much easier to manage and understand. It's like sorting your books by genre instead of just having a big pile. It's much easier to find what you need. This is where things get really interesting. Different subsets of real numbers behave differently when you perform operations on them. For example, if you add 2 integers, you always get another integer. But if you add an integer and an irrational number, like the square root of 2, you'll get an irrational number. Understanding these properties within each subset is crucial for doing algebra, calculus, and more advanced math. When you're tackling a math problem, often you can simplify things significantly by focusing on a specific subset of real numbers. If a problem specifically mentions whole numbers, you don't need to worry about fractions or decimals. This narrows your focus and makes the problem much more manageable. It's about using the right tools for the job and knowing which numbers fall into which categories. So let's move on to slide 5 and discuss why understanding these subsets of real numbers is actually important. So, these aren't just abstract concepts. They're fundamental to how we approach and solve mathematical problems. Now, let's move on to the next slide, where we'll recap the key takeaways from this introduction. Key takeaways. Remember, when we talk about a set, we're simply grouping things together. And by distinct, we mean that each object within the set is unique, no repetitions allowed. We use those curly braces, like we saw with the vowels, to show what belongs in the set. So, if you have a larger set, a subset is just a smaller group taken from that larger set. Every item in the subset must also be in the bigger set. Think of it like this: all dogs are animals, so the set of dogs is a subset of the set of animals. The set of real numbers, denoted by \mathbar$, includes absolutely all the numbers you can think of that can be shown on a number line. That's positive numbers, negative numbers, zero, fractions, decimals, everything. The symbol, which is a stylized capital R with a double bar, is how mathematicians write the set of all real numbers quickly. We say it as R. This is where things get really useful. We don't just leave all the real numbers jumbled together. We group them, like even numbers, odd numbers, prime numbers, rational numbers, irrational numbers. Each of these groups is a subset of the real numbers. Understanding these subsets will help us solve problems more efficiently and understand how numbers behave in different mathematical operations, which we'll explore in future lessons. Let's recap what we've covered so far. This slide, titled Key Takeaways, summarizes the most important points about sets, subsets, and real numbers. So, keep these 4 key takeaways in mind as we continue. They form the foundation for understanding more complex concepts in mathematics. And remember, we'll be building on this knowledge, so it's important to have a solid grasp of these basics. Common mistakes. Let's move on to this final slide, which highlights some common mistakes students make when working with sets and subsets. This is really important to understand so we can avoid those pitfalls as we move forward with more complex concepts. So, the first point here says, confusing a subset with an equivalent set is common. Now, remember from the previous slides, we defined a subset as a collection of elements contained within another set. 2 sets are equivalent, or equal, only if they contain exactly the same elements. It's a subtle but crucial difference. The next line clarifies this. A subset contains some or all of the elements of another set, but not necessarily all. Think of it like this. If you have a big box of crayons, a smaller box with just a few of those crayons would be a subset. It's still made up of crayons from the bigger box, but it doesn't need to have every crayon. It could have just a few, or even all of them. Finally, let's look at the example. It states, the set containing 1 and 2, written as 1, 2, is a subset of the set containing 1, 2, and 3, written as 1, 2, 3, but it is not equal to it. So every element in the set 1, 2, which is 1 and 2, is also found within the set 1, 2, 3. That makes 1, 2 a subset. However, 1, 2, 3 has an extra element 3 that isn't in 1, 2. Because they are exactly the same, they aren't equal sets. Understanding this distinction between a subset and an equal set is key. We'll be building on these ideas, so make sure you've got a firm grasp of it. Are there any questions about this before we wrap up this introduction to subsets of real numbers?